So now that we've looked at the half transform, I want to come back to instance segmentation and add the probably most important range of techniques for bottom-up instance segmentation, namely by means of similarity learning. So where's the connection to the half transform that we've just been discussing? I had just been saying that we can take a local patch, such as this one, and have this patch vote directly for, let's say, an angle and a distance from the origin. And then this patch may vote for here. And a different patch from the same line may vote for there. A patch from the other line may vote here. And the patch from the area where the lines cross will probably be completely confused and make, cast some strange votes anywhere. Now, the nice thing so far was that what we put in as prior knowledge was the kind of shape that we're looking for, a straight line. This also works similarly for circles and other parametric objects, but no training data was needed. So, good thing, no training data needed. The bad thing, well, this is limited to pretty simple parametric objects. But now we want to solve complicated problems, and we do assume that we have some ground truth annotations. So for example, the annotation that all of the pixels that are marked in red, they belong to one instance, and all the pixels that are marked in blue correspond to another instance. And now the question is, can we exploit this knowledge to somehow learn a vote casting? And here we don't really, if ultimately the aim is that we want to distinguish any number of line segments that overlap each other in the image domain, if this is the ultimate aim and we don't really care about angle or offset or any such thing, then we can abstract the task one step further and say, all right, let's directly use this information to say that this mapping should be such that all the red pixels end up close together in some space and all the blue points end up close together in some space. This is the fundamental idea, and this is what we're now going to do again and again in this part of the lecture. Okay, I'll give you a more complicated example. Here are my much loved neuron images. So we can train a convolutional neural network to take a pixel and its local context, so to take a patch and to embed it somewhere in a parenthesis half space. These spaces that we use are often 8 or 16 dimensional, but we can still try and that's a bit difficult to plot here, but we can project them to a low dimensional space such that we can show by color where they get mapped. So here, for example, image courtesy of Roman Remme, we take an image patch such as this one here, and we map it to a point that you here see characterized by its color. Now for this type of data we have ground truth. So the ground truth tells us that, for example, any 2 pixels in here should get mapped to the same point in space. Now, if you look what the neural network does do, the colors here and the colors there, they're not perfectly the same. They're similar, but not the same. So for neural network training, because we know that according to the ground truth, these have the identical color, we can now use a pull loss that will change the neural network parameters so as to make these embeddings more similar to each other. Now, if we only had pull losses, then we would end up with the same color throughout the image. So of course, we also need a mechanism that will take two pixels that belong to different instances and look at their colors. So here we have two instances. Sorry, they're hidden under my picture. We have two instances side by side. They have different color, and yet in the embedding, they're sort of the same color. So here we would use a push loss to encourage a neural network to give more distinct colors to these two pixels. Again, note that the colors on the right-hand side, they are completely arbitrary. So you will see that some neighboring colors like these here are more similar to each other than other adjacent colors like those. But there is no meaning in these ground truth colors. The only question is, are the colors identical or different in the ground truth? Whereas here in the middle, similarity or dissimilarity, or all these hues do matter, and we try and imitate a ground truth as best as we can. It's not important, let me repeat, it's not important that the neural network predicts the same colors as the ground truth. The only thing that we respect is, are two pixels colored the same way or not as they should be in the ground truth. So in other words, this region here is green in ground truth and it is brown in our prediction. We don't care. What does matter is that any two pixels within that region should have the same color of brown, because they have the same color of green over there. Also, what does matter is that any two pixels from distinct regions, so any two pixels which have different color in the ground truth, they should also have different color in the prediction. All right. Now, these color, actually the neural network is a little bit better than what you see here. So these color variations across a segment have been artificially enhanced to make them more visible, but still, if we make a different kind of plot, so this is now a two-dimensional projection of this high-dimensional space, we see that the points from one segment, and each segment here has many thousand of points, they mostly cluster nicely together, but we also have some pixels of mixed color. Actually, there are not many, because on the left, this image is maybe 250,000 pixels. So then we have 250,000 points here, and most of them we don't see. So most pixels are actually nicely clustered, but not all. And this is why we need an additional clustering step to make things crisper. Or in the spatial domain, it looks like this. Unfortunately, in the dimension reduction here from left to right, the colors, they look very different now. But the important thing is that here they are more homogeneous than they are on the left. Okay, so that was the big picture. Now let's look at this in more detail. So rather than directly learn whether two pixels are similar or dissimilar, what we learn is a mapping from the observations, from the image, into some embedding space, which, as I've said, is maybe 8 or 16 dimensional. And then we can compute a similarity between two pixels or patches by computing the distance or how close are the embeddings associated with these two patches. And well, that, as the last comment on the slide says, is very computationally efficient, because we just need to compare something like Euclidean distance or use some other metric in this embedding space. So we only need, we only need to embed each pixel once. It's linear in the number of pixels, the embedding that we create. And then we can indeed use the kind of ground truth that I've sketched earlier up. So what you see here on the left are two different inputs, and you want to train the neural network to find instances. Now, for traditional computer vision, that is not a trivial task, because we consider this and this to be the same instance, but it's occluded by something else. So if we did do something like find all boundaries and then do connected components, then because we have this occlusion here, the occlusion would split my part into two halves, one left and one right half, but we want it to be the same. So here, some ground truth is being used, and note that here and here, the ground truth has the same color. The color is arbitrary, but what matters is that it's the same. And then the neural network is trained to predict n embedding for each pixel, which is again visualized as color here. And you see that indeed very similar embeddings, very similar colors are being produced for these two halves of the same instance. Now, how to do that? I've mentioned this pull and push loss. So let's look at this formula here for contrastive loss or associative loss. We have a summation over all pixels or patches, or over all pairs of pixels, over all pairs of patches in the image. In the stochastic gradient descent sense, of course, we don't take into account when I have a million pixels, a million times a million, I would have 10 to the 12 terms here. I don't use the 10 to the 12 terms, but I only use a few in every gradient descent step. So these few would make up my mini batch, hence we do stochastic gradient descent and not full gradient descent. Okay. Then we can, if we want, associate each pixel with weight. And then we want pixels that belong to the same instance, we want them to be very similar. Yeah? So what we have here, this Kronecker delta, it is 1 if Ci is Cj and 0 else. So if the two pixels belong to the same instance, then this part of the loss is turned on. And we have here the similarity. The similarity, which is here assumed to be 0 and 1. And E of xi, that's the embedding associated with xi. E of xj is the embedding associated with xj. So in other words, if two pixels I and j are from the same instance, then to minimize the loss, we want their similarity to be large. And vice versa, that's the second half of the equation. If Ci and Cj are from different instances, then we want their similarity to be small. It doesn't have to be precisely 0. So you see what we have here is the similarity minus some constant alpha, and then the plus here says that we rectify. We only keep the so this is s minus alpha if s minus alpha is larger than 0, and it is 0 if s minus alpha is less than 0. Okay, so we retain only the positive part of this expression here. Good. This is the associative loss. Fairly straightforward. And let me ask if you have any questions for this associative loss. Okay, when there are no more questions, let's go on to improvement. The segment-wise contrastive loss empirically works better than what we have just discussed. So here, well, why does it work better? Because let's look at this point here. By the push-pull loss, the blue one, by the pull loss, the blue one gets attracted to the other blue ones, but by the push loss, so if, for example, I compare the blue, this one, with all the purple ones, it will get a net force of something like that. Yeah? So the pull loss does the right thing, but the push loss somehow sends this in a weird direction. And this is why you can instead use a segment-wise contrastive loss. So the pull term says that each instance is pulled towards the center of mass of the votes associated with that instance. But the push loss acts on the centers of mass. Yeah, so green in this slide here represents attraction. So at train time, each pixel is trained to become, or the embedding of each pixel is trained to become more similar to the embeddings of all other pixels from the same instance. That's attractive. And then push means that the centers of mass repel each other. As I said, works better in practice. Then I want to talk about the triplet loss. So the model that we've seen here, the pull loss always tries and make a single class very compact in this latent space. But sometimes that is too much to ask. So here, for example, in the ground truth, the red thing is considered one instance. But if you look closer, you know, we have a motor scooter and a person, and you can argue, especially if you're also working on detecting people in the same benchmark, that it's quite okay for the rider pixels to be embedded a bit further from the scooter pixels, even though they form one instance. And so in this triplet loss, what you do is the following. For a point of interest, such as this one, you find the closest pixels from the same class. So the closest neighbors from the same class, if I'm looking for the 3 closest neighbors and then connecting them with green, it's probably this one and maybe that one. And who's the winner? Is it this one or is it the other one? Let me pretend that it's this one. So this current point of interest, or anchor, that's the anchor here, you look for the closest members of the same class and you pull the anchor towards those closest members of the same class, and you identify the closest members of a different instance. So the closest 3 from the different, instance would be this one and that one and that one. And then you push it away from those others. And the advantage here is that, well, you only ask that, or each anchor only gets attracted by its nearest neighbors from the same class. It does not have to be close to every pixel of the same, I always say class, that's wrong. It doesn't have to be close to every pixel from the same instance. So the instance should be contiguous in this embedding space, but it needs not be compact. And that makes the learning task a little bit simpler for the neural network and maybe more meaningful. All right, what are variations on this theme? You can, something that's really interesting is to directly supervise some dimensions of the embeddings. So, for example, in problems like the yeast cells, one possibility to give ground truth is by coloring, by saying this is my green instance, and this is my blue instances, and this is my red instance. This is one way of providing ground truth. And then all we ask the embedding is to get similar or dissimilar. But you could also, from this ground truth, compute what are the respective centers of the instances. And then you could train, so for example, if we have a 16-dimensional embedding vector, you could use 2 of these dimensions to always estimate where the center of that instance is. So you could use the associative loss, for example, as just described, on 14 dimensions, but 2 dimensions you could use to try and directly point to, for example, the center of that instance. So that would add some amount of geometric supervision here. And this kind of direct supervision you can use to do all kinds of things. So in this paper, for example, what's asked here is you ask for each point in an instance in which direction the closest boundary lies. So in the ground truth, we ask for any pixel in which direction does the boundary lie, and so that gives you an angle for each pixel, and the ground truth angle is shown here. And then you can, well, just learn that in a supervised fashion. So that would be a regression problem. And this you can combine with the purely associative loss that we have just discussed. And this kind of supervision, so here in this type of image, the task was to estimate the distance to the closest boundary. And this is the ground truth, and this is the estimate. And then you may get extra cues that may help you in segmenting your image. All right, this is what I wanted to say about this similarity learning. Bottom line is neural network produces embeddings. These embeddings are then clustered into instances. We don't care what the embeddings themselves are. We only care about the similarity of pairs of embeddings, and we try and make these match to ground truth. So it's interesting in the sense that when I try to explain to people not from computer vision what we are trying to do on these very large-scale neural images, I always said, well, it's like drawing in a coloring book. You just try and give one distinct color to each segment. And well, this is literally what this line of work does. And it does not matter which color you use. The only thing that matters is that you use the same color for all pixels from one segment and different colors for pixels from adjacent segments. And this fact that it doesn't matter which sets of colors as long as they're same or different means that the neural network somehow breaks this degeneracy. And this is why initially I was skeptical of this line of work, because I thought, there is this degeneracy. How can the neural network learn to break it in a meaningful way? But the fact is that it does, and I would say it's not yet really understood why that is so. Good, thank you.